We've previously explored heart rate variability, HRV, and the distinctions between coherent and incoherent patterns. Make sure you check the previous clips. This naturally leads to the question, what underlies these patterns from a signal perspective? To examine deeper, we'll shift our focus to the mathematical properties of waves and signals. By examining these foundational concepts, we aim to better understand why certain HRV graphs are deemed coherent while others are not. This approach will help clarify the nature of HRV coherence through the lens of signal analysis. Let's explain this. A complex signal can be formed by combining simpler signals. Let's explore this by adding two sine waves. For example, first wave, 2 Hz sine wave, second wave, 4 Hz sine wave. When these two signals are added, the resulting signal is a combination of both. This means that at every point in time, the amplitudes, heights, of the two waves are summed together. The resulting waveform is more complex and exhibits characteristics from both original waves. This principle is fundamental in signal processing and helps in understanding how complex signals are formed from simpler ones. Let's proceed by adding more signals. Previously, we discussed sine waves at 2 Hz and 4 Hz, which, when combined, produce a specific waveform. Now, let's add a third sine wave at 7 Hz. The resulting waveform is the summation of the 2 Hz, 4 Hz, and 7 Hz signals. While this composite signal is more complex and less consistent than the individual sine waves, it still exhibits a harmonious pattern due to the mathematical relationships between the frequencies. Next, we incorporate a fourth sine wave at 13 Hz. The addition of this higher frequency further enriches the waveform, introducing finer details and increasing its complexity. Despite the added intricacy, the resulting signal maintains an underlying harmonious structure, illustrating how multiple sine waves can combine to form rich and complex waveforms. When a signal, such as a sound or HRV measurement, is presented, it is typically a composite of multiple frequencies. Through a mathematical process known as the fast Fourier transform, this complex signal can be decomposed into its individual frequency components. In HRV coherence analysis, the process begins with acquiring the HRV signal, which is then filtered to eliminate artifacts and noise, ensuring accurate analysis. Subsequently, the fast Fourier transform is applied to decompose the signal into its constituent frequency components. Coherence is identified by detecting a narrow, high-amplitude peak in the low-frequency range, typically around 0.1 Hz, indicating a harmonious balance between the sympathetic and parasympathetic branches of the autonomic nervous system. A coherence score is calculated using an algorithm that assesses the stability and amplitude of the 0.1 Hz peak over time. This score reflects the degree of physiological coherence, independent of heart rate and HRV amplitude, making it applicable across different age groups. I'm Well Guru, thank you for watching. I'll return with more in-depth insights on HRV signal processing. Until next time, goodbye.